All right. Good afternoon. So today we are going to continue on 1 degree of freedom system, free vibration, but we have damping on the system. Um, any question for this stuff? After we cover this, we can have our first exam. I'll let you know about that video. Um, so if we have a simple mass spring damper with a stiffness of K and damping constant of C, the equation of motion is going to look like this. So we could find the response of the system it's gonna look like this: C1 e power S1t plus C2 e power S2t, where S1 and S2 are the roots of this quadratic equation, which is gonna be negative C plus and minus a square root of C square minus 4mk divided by 2m. Which can be written as negative C divided by 2m plus and minus C over 2m square minus K over m. Then you move 2m inside, it's going to be 4m squared, 4 can be cancelled out, and we are going to have this K over m. So we define CC as a critical damping constant. It's a damping constant at which inside the square root is going to be 0. So if I set that equals to 0, CC would be 2m square root of k over m, or 2 square root of km. These are the same, or 2m omega n. These are what we covered on last class. And we defined zeta as a damping ratio, which is C over Cc. So if I want to rewrite S1 and S2, as a zeta, C over zeta is C over Cc, and Cc is 2m over omega n, so C 2m omega n. So C over 2m is gonna be zeta times omega n. So I'm gonna replace C over 2m by zeta times omega n. I'm gonna get negative zeta omega n plus and minus C over 2m is gonna be zeta squared omega n squared minus k over m. Omega n is always s square root of k over m. So k over m is omega n squared. So if I take omega n squared out of the square root, I'm gonna get omega n times negative zeta plus and minus a square root of zeta squared minus 1. So the roots can be written as a omega n and zeta. Good? we just derived those things on Wednesday class. And now, here, I would like to write this as a negative 1 times 1 minus zeta squared. So this inside the square root can be written as negative 1 times 1 minus zeta squared, or square root of negative 1 times 1 minus zeta squared. And we know that I is going to be square root of negative 1. So I can replace this by omega n times negative zeta plus and minus I, instead of this, I times 1 minus zeta squared. So then if I replace this S1 and S2 in this general solution, I'm going to get x, x of t equals to C1 e power C1 e power S1t, which is negative zeta plus I 1 minus zeta squared omega nt plus C2 e power negative zeta minus I, the square root of 1 minus zeta squared omega nt. And this is the term that we are going to use for the response of the system. Everybody can see how we derive the response of the system. All right, now we are gonna look at 4 different cases. 1, these are the cases that we are gonna look at. Case 1, zeta equals to 0. When, if zeta equals to 0, C should be 0. If C is 0, we should end up to the response of the system where we had no damping on the system. We already covered that response. So case 2, zeta is greater than 0, but it's less than 1. We call it under damped system. Case 3, if zeta equals to 1, we call it critically damped. And we find the response of the system for case 3 as well. And case 4 is zeta is greater than 1, overdamped. So we would like to know, for this general response of the system, if any of these cases happen, what would be the response of the system? All right, I will start with case 1. Case 1, zeta equals to 0. just plugging theta equals to 0. This term is gone. 1 minus 0 would be 1. I times the square root of 1 is going to be I. C1 e power I omega nt plus C2 e power negative I omega nt. So the response of the system is going to look like this. Just recall e power I theta or I omega nt is going to be cosine of omega nt plus I sine of omega nt. If I plug in here, I do it once, but I'm going to use it later. So next time I'm not going to derive the equation. So x of t is going to be c1 times this c1 cosine of omega nt plus I c1 sine of omega nt plus c2 cosine of negative omega nt plus I C2 sine of negative omega nt. This has negative omega n, omega nt, I just replace them. Cosine of theta equals to cosine of negative theta. So this is going to be same as this. And sine of negative of theta or whatever is the angle is going to be negative sine of that angle. So I move this negative here, this negative is going to change to positive. So these two are real number, I can add them up. So I'm getting C1 plus C2 cosine of omega nt plus C1 minus C2 sine of omega nt. Makes sense. Here I have real number. Right here I have imaginary part. Since it's a real thing, x of t is a real thing, so I'm gonna assume that C1 equals to A plus IB, C2 equals to A minus IB. The reason that I'm assuming them, because if I add them up, if I add C1 and C2, I will get A to A, IB, it's going to be cancelled out. For the negative, I'm getting C1 plus C2 would be 2A. C1 minus C2, I'm getting A, it's going to be cancelled out, I'm getting 2IB. C1 minus C2 is going to be 2IB. And C1 plus C2 is going to be 2A. So 2I times I is going to be 2I squared or negative 1. I times I is going to be negative 1. So it's going to end up to 2A cosine of omega nt minus 2B sine of omega nt. And then 2A is a constant or coefficient, I convert the A. Negative 2B is constant, it's going to be capital B. So the response of the system is going to look like this. And this is what we were supposed to get. This is what we did for free vibration where we had no damping resistance. We end up to something like that. Two harmonic function, we can add them up, end up either to something like this or something like this. Either sine function or cosine function, it's up to you. Anyway, it's kind of an arc is s square root of a squared plus b squared. And v was tangent inverse of b over a. Just good. We were supposed to get the same result that we derived for no damping system. Now, case 2, which is yes. Case 2 for overdamped. Sorry, underdamped system. When we have zeta value between 0 and 1, this ratio. The response of the system is going to look like C1 e power look at this. This one has C1 e negative zeta omega nt e power negative zeta omega nt. I'll take these two negative zeta omega nt out of the bracket. The left is going to be C1 e power this plus C2 e power this. So I just took this common term e power negative zeta omega. Unlike here, now look at this. We had C1 e power I omega nt, C2 e power negative I omega nt. We could end up to something like this. So compare this with whatever we have here. C1 e, this part square root of 1 minus zeta square omega nt is going to be this. E power negative of that is going to be this, and both have I. So this summation is going to end up to like this. So x of t is going to be e power negative zeta omega nt. Inside the bracket, I'm going to have this a cosine. Omega nt was this guy. I should have this term for here. 1 minus zeta square omega nt plus b sine of square root of 1 minus zeta square omega nt. And it's for the case where we have zeta between 0 and 1. Good? Alright. Now, how can we find, here we learned how to find A and B. We need two initial conditions. For example, at time 0, what would be the location of the mass M, mass M, and what would be the velocity of that. So we apply initial condition. X at time 0, we call it x naught, and velocity at time 0, for example, we call it v naught. The initial condition can be different, but for this initial condition, we can find A and B. Just plug in time equals to 0. E power x naught would be e power negative zeta omega m times 0 a cosine of 1 minus zeta square omega n times 0 plus b sine of 1 minus zeta square omega n times 0. I just replace time by the value of the 0. So e power 0 is going to be 1. So 1 times a times cosine of this times omega n times 0. It's going to be cosine of 0. Cosine of 0 is going to be 1. So 1 times a would be 1, a. And sine of 0, it's going to be 0, so b times 0. So this is going to be equals to x naught. So a plus 0 would be a. I can find that a should get the value of x naught. Finding a was easy. So finding b, I need to know the velocity. To find the velocity, I should differentiate this. So x dot of t would be derivative of this times this plus derivative of this times this. If we do that, I can show the steps, but it takes time. So, what we need to do is to find the velocity. If we do that and set times equals to 0 and set it equals to v naught, we can solve for b because a is already x naught. So we can find b equals to v naught plus zeta omega n x naught omega n 1 minus zeta square square root. Good. All right. Now what I'm gonna do? I'm gonna plug in this A and B here. So I'm gonna get x of t equals to e power negative zeta omega n t multiplied by A, which is x naught, times cosine of square root of 1 minus zeta square omega n t plus b. B is this guy. V naught plus zeta omega n x naught omega n 1 minus zeta square cosine of Sine of, sorry. Sine of s square root of 1 minus delta square omega n t. And that's it. So for any given time, I'm asking you where is the location of x at time point 1. You plug in point 1, omega n is the specification of the system, s square root of k over n. Zeta is the c over cc, it's c over 2m omega n. C is the specification of system, m and omega n are the specification of the system. So you can find this. X naught is initial condition. Here you calculate cosine of this term by plugging time equals to 0.1. Same things here. V naught is initial condition, and we can find x of t at any specific time. So here again, I have cosine of one angle like this, sine of one angle like this. So I can add them up inside the bracket and come out with this. X of t equals to e power negative zeta omega n t multiplied by capital X times sine of 1 minus zeta square omega n t. This is A, this is A, this is B. I have A cosine plus B sine, A cosine plus B sine. Summation of two harmonic function can be written as a sine or cosine function plus B sine. I forgot. And what are the value of the phi? X would be s square root of a square plus b square. This is A, this is B. And phi is tangent inverse of A over B. And this is the general solution for underdamped system where zeta is between 0 and 2. Any questions so far? Alright, now for case 1, where zeta was equals to 0, where we had simple harmonic function, summation of two harmonic function, it's going to end up with a sine function with no dampings. The motion is going to look like this. One harmonic function is going to go forever if this is the time, if this is x. So this x of t over the time is going to look like the sine or cosine function. Now let's look at this function. If I then have this exponential function here, inside the bracket I have coefficient, amplitude, and sine function, which is going to look like this. But this term is going to show up due to the zeta that we have, due to the damping that we have, and it's going to change the response of the system. Now let's see how it's going to look like. This is x, this is t. Let me show you this. So over the time, this motion is not gonna die. So it's gonna, this motion is gonna repeat itself over the time. But for underdamped system, it's gonna start at somewhere x1 at time 0. When you plug in time 0, you will get this point, and then it's gonna start having something like harmonic function, with one difference, that the motion is gonna die over the time. So after passing the time, the amplitude is gonna be it's gonna converge to the 0. So this is a big difference between case 1, which is a non-damping system, and under-damped system. So here we can see the motion is gonna decrease over the time. Another thing, if you try to plot a curve which is tangent to the peaks, just look at the peaks and plot a curve which is tangent to the peak. The function of this is going to look like this: x e power negative zeta omega nt, which is this e negative zeta omega nt times the amplitude. This is going to be the function for that curve. So this is another thing. I mean, this phi is going to be the angle that we calculated here. And what else? I'm gonna define a new term, which is gonna be period of oscillation for damping system, TD. So we have period of oscillation as T, which was 2 pi over omega n. I'm gonna define another term for underdamped system as a TD, 2 pi over omega d. So I think on last Wednesday class we defined omega d, but if it didn't, omega d is defined as omega n square root of 1 minus zeta square, and we call it angular frequency of damping system. So let me write. Sometimes we call it as a natural frequency. As I said, it's an angular frequency, but angular frequency of damping vibration. This is going to be omega d. It's a function of omega n and the zeta. And if you have omega d, you can find period of oscillation for damping system. It's a time which takes between 2 peaks or 2 same points. For example, this point and this point are the same, so the time difference between these two is going to be Td. And how much would be that time? 2 pi over omega. Good? These are some, we are going to use these details on different examples on the maybe exams problem. So make sure that you don't get confused, because I defined different terms. All right, let's look at case 3. Case 3 is a special case where we have zeta equals to 1. So this is the general solution that we derive. So case 3, it's critically damped. Zeta equals to 1. The ratio is equals to 1. You remember how did we find the roots? We find the roots from this quadratic equation. The S1 and S2, it's gonna be it was negative zeta plus and minus s square root of zeta square minus 1. So as you see, for zeta equals to 1, inside the bracket is going to be 0. So plus and minus 0 is going to be the same. So we have repeated roots. S1 and S2, they are going to be the same. We're going to get the value of the negative zeta. So in differential equation, because we started with this equation, these are the response of this system. On the second order differential equation, when we have repeated roots, the response is going to look like this. C1 plus C2t e power negative omega n t. Here, if you plug in zeta equals to 1, you will get 0 here, you will get 0 here. So it's going to be C2 times 1, C1 times 1. So if you do that, you are going to get one response. But we know that when we have repeated roots like this, one term with the value of C2t is going to show up. T is the time. And how can we find C1 and C2 initial condition? So if I differentiate this with respect to time, it's going to be negative C1 omega n e power negative omega n t plus C2e negative omega n t minus C2t omega n e power negative omega n t. So at time 0, if you plug in time 0, this term is gone. C1 times e power 0, it's going to be C1. So C1 will be x naught. So x naught is given. We should find C2. I'm going to plug in time equals to 0. If I plug in time equals to 0, I'm going to get e power 0, which is 1, negative C1 omega n plus C2 times e power 0, and here times is 0, C2 times 0 is going to be 0. So C1 is x naught. I can solve for C2. C2 would be V naught plus x naught omega n divided by 1, which is going to be this. So if I write the solution for case 3, x of t is going to look like this. X naught plus v naught plus omega n x naught times t summation is going to be negative omega n t. It's a coefficients times exponential function. Do you think that we are going to have harmonic motion here? It's not going to repeat itself because this is going to look like this. For sure, it depends on the sign of initial condition, V naught and X naught. So for V naught greater than 0, it's going to look like this. This motion, you are gonna have overshoot, and then it's gonna decrease, and it's gonna die. The motion is gonna die after. So as t goes to infinite value, x of t, it's gonna converge to 0. So depending on the sign of velocity, the response of the system is going to look like this for if the initial condition for the velocity is positive at time 0. If it's 0, it's going to look like this, if the velocity is 0. And if the velocity is negative, it's going to look like this. It's decreasing, it's going to be negative, and then it's going to increasing up to 0. Good. So we have aperiodic motion. We call it basically it's a non-periodic motion when we have critically damped. So case 4. It's happening when we have overdamped, when zeta is greater than 1. Now let's see how this is case 2, case 3, case 1. Let me get rid of case 1. Case 4. Case 4, zeta is greater than 1. So you remember what we did here. I is s square root of -1. So I can write s square root of -1 times s square root of 1 minus zeta square is gonna be s square root of zeta square minus 1. This is gonna be negative times this is gonna be this. So when zeta is greater than 1, inside the bracket, inside the square root is gonna be positive for this one. So this guy is gonna change to this. X of t would be e power negative zeta omega nt times c1 e power square root of zeta square minus 1 omega nt plus c2 e power negative if I multiply these two, e times e, I can add them up. So I'm going to get x of t equals to e power c1 e power negative zeta plus s square root of zeta square minus 1 omega nt plus c2 negative zeta minus initial condition x dot equals to x at times 0 we call it x naught, velocity at times 0 is going to be v naught. It's given. So how can we find c1 and c2? Just plug in time equals to 0 for displacement, for velocity differentiate set the time equals to 0, set equals to v naught, solve for c1 and c2. It takes time. You can find the C1 and C2 on the textbook.
Like we got the
Yes.
It's plus C2 e to that power.
C2 thanks. Okay. Yes. Look at C1 and C2 on textbook. It's a long expression for C1 and C2. So this motion also is similar to this. Case 3, critical jam. So it's gonna be, it's not harmonic motion, so it's gonna be something like this. It's not gonna repeat itself over the time. Any question? All right. So let's look at this one. Look at this simulation. Suppose we have this mass and a spring. Here I can play with the stiffness of the system. Damping is not going to show up, but you can change the value. At this time it's going to be 0, and the mass, it's going to calculate the frequency of the system. So if I have no damping system like mass and a spring, it's going to look like a sine or cosine function like this. Now I would like to go over, let me increase the stiffness. You can see how it's going to look like, and increase the mass. Now I'm going to give it some damping. Let me see what's happening after I increase some damping. It's gonna oscillate, and then it's gonna die after a while. So let me give it more mass. Give it some mass, some damping. The motion is gonna look like this. Now I'm gonna look at the critical damping, case 3. Set it 0, and now I'm gonna click on critical damping, see how it's gonna look like. It's gonna start from here, and it's gonna die, and it's not gonna repeat itself, the motion. And critically damped, let's see. This is critically damped. It's very similar to the function of, it's overdamped, sorry. The function is very similar to critically damped, just maybe, for example, with this difference. So if this line is representing critically damped, like this, you see that the motion is going to die. You don't see any motion is going to be repeated. So it's not periodic motion. And overdamped is going to look like the dashed line, like this. The functions are the same, just different height here, different peak, and it's just a little bit different. The other two motions, case 1, no damping, it's gonna look like this. When zeta equals to 0 undamped. So as you see, the motion is gonna repeat itself. The time between two corresponding point is going to be 2 pi over omega. You can consider either peak or any two corresponding points. For example, this point and this point. The time lag is going to be 2 pi over omega. This is period oscillation. For underdamped, which is case 2, zeta is between 0 and 1, we have a dashed line. It's going to look like this. As you see, the peak or the motion is decreasing and it's going to die over the time. So again, if you pick two same points, suppose 2 peak, the time difference between these two is 2 pi over omega d. Omega d was natural frequency of or angular frequency of damping vibration. So this is how we can show all 4 cases here. And as you see, omega d is omega n times this square root. And since zeta is between 0 and 1, 1 minus this is going to be less than 1, multiplied by omega n is going to be less than omega n. So omega d is smaller than omega n always for underdamped. Make sense? All right. And one more thing about case 3, critically damped, when zeta equals to 1. Cc is the shortest damping constant, which makes the motion, we change the motion to the non-harmonic motion. So if you want to know what would be the shortest value to make a harmonic motion to the non-harmonic motion, Cc is the shortest value. So the smallest value which changed the harmonic motion to non-harmonic motion or to non-periodic motion is going to be Cc. And as you see, if you have critically damped, you are going to have a small overshoot. It's going to increase the X. But after that, the mass is going to back to the rest position, which is X equals to 0. So this is what's happening when you have critically damped system. So it's the smallest value that you can have to have the smallest overshoot, and the mass is going to back to the rest position in the shortest period of time. And what else? If you have non-periodic, if you have underdamped system, you still have periodic motion because it's going to repeat itself, but after time, after passing the time, the motion is going to die. All right, let me stop at this slide because it's going to take time to start. So we continue on Wednesday class.
We don't have to switch to break.
No, it's going to be the Wednesday after the break or
Okay.
Monday.
Alright.
Not after the break. If it's Monday, it's going to be 2 weeks.
It's like Wednesday and we'll break.